Okay, so welcome to the 34th video in the Discrete structure series, and we have been covering our chapter of induction and recursion. We have finished talking about induction, and inside of recursion, we have looked at recursively defined functions, sets, and structures. And continuing from this point, the goal of today's video is going to be structural induction. And structural induction is a method to prove results about recursively defined structures. For example, yesterday we discussed the well-formed formula in propositional logic. And we also gave the example of an invalid formula like P, Q, and. And we said that a well-formed formula cannot have a conjunction at the end. But how can we actually prove that? Another example, I know that every well-formed formula has equal number of left and right parentheses. Because if the number of left parentheses is not equal to the right parenthesis, the formula is not well-formed. So I might want to prove that every well-formed formula derived from yesterday's definition have an equal number of left and right parentheses. Yesterday under recursive structures, we looked into a few kinds of trees. I might want to prove certain properties about the vertices and edges of those trees. So whenever it comes to a situation like these, when we need to prove any aspect about a recursively defined structure, the process of structural induction comes into play. And this goes without saying, the understanding of structures is important before we start to dive into this topic. Because you have to know what a well-formed formula is before you can prove some result about a well-formed formula. You have to understand what a tree is before you can prove a result about a tree. So I'll make sure to revisit and recapture some concepts when needed, but it would be ideal if you are already somewhat comfortable with recursive structures from yesterday's lecture. And with that said, let's dive into the main agenda of the video. We'll start with discussing the steps of structural induction. So in order to prove any fact about a recursively defined structure, we follow these steps. So let us remember what the first step in recursion was. The first step was called a basis step. In case of a function, this was the value of the function at some initial points. In case of a set, the basis step provided a few starting elements. In case of well-formed formulas, we provided what the simplest forms of well-formed formula look like. In case of trees, we defined the simplest kind of trees. But whatever structure we are defining with our recursive definition, in order to prove a fact about that structure, we need to prove that fact for all the elements given in the base step. So when I'm writing basis step here, I'm writing the basis step of my proof using structural induction. But you should understand that the recursive structure that I'm trying to prove this fact about has a basis step on its own. And the basis step of my proof is the process of showing that the property is true for every base case of the recursion. And let's try to find the analogy with the second step. So when providing a recursive definition, in the second step, we provided how to produce new elements based on existing elements. So in case of functions, we provided a rule to calculate the value of the functions based on previous values. In case of trees, we had a rule to build new trees based on existing trees. For well-formed formulas, we built new well-formed formulas from existing formulas. So the second step in the recursion was essentially a rule to do that. And now in this context, when I'm trying to prove a fact about elements generated by that recursion, I want that particular fact to be true for all new elements generated by the recursive definition. Therefore, the second inductive step of my proof involves showing that the fact or property is true for every new element generated using the recursive definition. And this just means that we need to prove that if we take existing elements and apply the recursive definition, the new elements that we get should also follow the fact or the property. Alright, so let's get into doing some problems, and this will be more clear hopefully. So the first question that we're going to do is going to be the continuation of one question that we did in the earlier video. So we had this question. So we were given a recursive definition, and this was for a set. It said that the element 3 belonged into my set, and it also gave me that anytime x and y belong to my set, their sum x plus y also belong to the same set. So earlier we just looked into this as an example, and we generated a few members of this set, and we kind of concluded without a proof that this is a set of multiples of 3. So today the requirement is to actually prove that. We need to prove that this recursive definition produces a set that contains the multiples of 3. And one thing I'd like to tell you immediately, this proof has two parts and only one part of it uses structural induction. And this is not your typical question in structural induction. We'll be looking into those questions after this, but this is an important question nonetheless, and the second half of its proof uses structural induction. Alright, let's make sense of this question. It is talking about two sets. The first one is this set, defined from the recursive definition, and it is asking me to prove that this set is the same as the set with multiples of 3. So let me assume another set which has all the elements like 3 times n, because this is a set with multiples of 3, and then I'll say n belongs to integers. So what I really need to show here is that the set S is equal to my set A. And if you have any experience proving equality of sets, you know that we do it in 2 steps. So we are given our sets S and A. The first step that we want to prove is that S is a subset of A. All elements of S are in A. And the second thing that will prove is that A is also a subset of S. And if we are able to show both proofs, it will mean that all elements of S are in A and all elements of A are in S. So they must be exactly equal. And before we do these two proofs, we could do it in any order. The important point is to be able to guess which of these proofs will use structural induction. In which case am I proving a fact about a recursively defined set? You see, A is not a recursively defined set. I've defined A as a multiples of 3. It's just 3 times n with any integer plugged. So if I put 100 here, it's just 300. But on the other hand, S is a recursively defined set. So in order to prove that S is a subset of A, I'll need to show that every element generated using this rule is a multiple of 3. And that is the same as asking prove that every element generated by this recursive structure is a multiple of 3. So I'll be proving a fact about a recursive structure. On this side though, I'll be proving that A is a subset of S. And that is like proving every multiple of 3 can be obtained by applying these rules. And that process we do using normal mathematical induction. So let us complete this part first. So proving that A is a subset of S is the same thing as proving this proposition. So I want to prove that no matter what n I choose, the element of A, 3n, will always belong to the set S. So let's prove this using mathematical induction. The normal mathematical induction will have a base case. And here we are simply checking if P1 is true. We are already familiar with this. So P1 is just 3 into 1, that is equal to 3. And is there a way I can tell this element belongs to S? I definitely can, because 3 belongs to S is given to me here. So the base case holds. Now I want to make my inductive premise or the inductive hypothesis. So here I'll need to assume that for any integer k, pk is true, which is the same as asserting 3k belongs to S. This is what I'm allowed to assume. Now in my actual induction, I need to show that pk plus 1 is also true. So I need to use this fact in order to show that pk plus 1 is true, which is the same as showing 3 times k plus 1 also belongs to this set S. And let us show that this way. We can say that this is equal to 3k plus 3. And now can you look into this rule? This says that if X is in set and Y is in set, their sum is also in the set. Now 3 is in the set because I have it from here, and Y is 3k in my set. That is because of my inductive premise or my inductive hypothesis. So by looking into this expression, this is an X that belongs to the set and this is an element Y that also belongs to the set. Therefore their sum would also belong to the set S. So we have already proved that every element in A belongs to S. Now in the second part, we'll show that every element in S is also an element of A. And again, what is it that we're doing here? We want to show that every number that is generated by this rule will also belong in A. In other words, every element generated in this rule is a multiple of 3. And we'll do that using structural induction. And we just looked into the rules. There are going to be 2 steps. Do not worry, this is just for an idea. We'll be doing a problem formally next. But let's recall the core idea that we discussed. We need to show that for all the base cases, some property is true. And we need to show that for every new element generated, the property is also true. And in this case, the property that I'm referring to is that it belongs to the set A. So let's begin with the base case. I have 3. Does 3 belong to the set A? Definitely, because this is just 3 times 1. And since 1 is an integer, this belongs to the set A. Because you see, 3 times any integer belongs to the set A. Now in this step, I need to show that every new element generated using this rule follows this property. And how do we generate elements using this rule? We need to take 2 existing elements from the same set. So let us do that. Let us say that A and B belong to the set S. And remember that the goal is to show that A plus B has a certain property given A and B individually have that property. So what is the property that I'm talking about? The property that I'm talking about is that it is a member of this set A. So you should be extremely clear. We take 2 elements from my existing set S. Now I want to assume that the existing elements A and B already satisfy this property. And using that assumption, I need to show that A plus B, the new element formed in this set, also satisfy the property. So AB belong to S. So now we assume that AB belong to A. They already satisfy the property that I'm looking for. Now since I've assumed both A and B have the property of being divisible by 3, I'll just say A is equals to 3 times some K1 and then B is equals to 3 times some K2. And using this, I want to show that the new element A plus B that is formed using this rule also satisfy the property that I'm looking for. So A plus B is just equal to 3 times K1 plus K2. And we know that this sum K1 plus K2 is also an integer. So we can confidently say that 3 times something is a member of A. So how does this structural induction build its proof? What we've proven here is that 3 belongs to A. And anytime we have any 2 elements that belong to A, their sum also belongs to A. So basically this proof will guarantee that every new element that is generated will keep belonging into the set A. So every element in S belongs to A, and here we showed that every element in A also belongs to S. Alright, next we'll dive into a couple of problems that are purely from the topic of structural induction. Prove that the formulas given by the following definition have equal number of left and right parentheses. So this is exactly the same problem that we looked at yesterday, and we know that it allows us to generate a family of well-formed formula in propositional logic. And today our goal is to show that every formula that is generated using these rules will have an equal number of left parentheses and right parentheses. So let's recall the process of structural induction from earlier. The first thing that will show is that everything in base case has an equal number of left and right parentheses, which should be obvious to see. It's just going to be a single true, a single false, or a single proposition. So none of them are going to have any parentheses in the first place, so the base case will hold easily. Now in the recursive step, we'll assume any two formulas P and Q that are well formed, and then we'll assume that they have an equal number of parentheses. And then we'll show that if we decide to apply one more recursive step with any of these rules, the resulting formula will also have equal number of left and right parentheses. And that will complete our proof. So let us show to make it more clear. We start with our base case. So everything that is given in the base case, true, F, S, where S is a single proposition, has 0 left parentheses and 0 right parentheses. So the number of parentheses is equal. Okay, so this is my base case. Now we'll go for our inductive step. So in the inductive step, we'll assume two well-formed formulas that already have an equal number of left and right parentheses. So let's say after applying this recursion k times, we reach two formulas A and B. And now we are entering the heart of the problem, and this is the most important thing to know. We want to show that if we apply these recursive steps one more time over A and B, the resulting formulas are still well formed. And that will be equivalent to saying that we started with a well formed formula, and anytime we merge it with any of these rules, we still get a well formed formula with an equal number of parentheses. So by assuming this, I'd want to prove that all of these things have an equal number of parentheses. So let me reiterate. I want to be able to prove, and let us list all the ways of combining A and B. For negation, we'll just use not A and B, A or B, A implies B, and then A by conditional B. We need to prove that all of these have equal number of left and right parentheses. And I don't want to forget there are parentheses here by definition. Okay, so how can we assume this and then prove this? So let us approach it this way. Let us assume the number of parentheses in A and B that are already existent. So let LA, RA, LB, RB be the left and right parentheses in A and B respectively. Then by my assumption in the inductive step, I have assumed that A and B have equal number of left and right parentheses. So that means I can guarantee that the left parenthesis in A is equal to the right parenthesis in A, and I can also guarantee the same for B. And now we'll look into the various ways of combining A and B and count the number of parentheses and so they are equal in each case. So if we look into the case of not A, how many left parentheses would it have? See, A already has LA left parentheses, and one more is added here. It has LA plus 1 left parenthesis, and what on the right? It's similarly just going to be the count of the right parentheses of A plus 1 plus this one. So it's just going to be right parentheses of A plus 1, and that's going to be the count of the right parentheses. Can you show that this number and this number is equal? Obviously, since LA is equals to RA, LA plus 1 would be equal to RA plus 1. And we would just say, since the left parenthesis of A is equal to the right parenthesis of A, this implies that LA plus 1 equals to RA plus 1. And then we form one another case for everything else. And everything else, we mean everything except this. I want you to list all of this here. I'm just being lazy, but the same rule will apply. So what is the count of left parenthesis here and what is the count of right parenthesis here? And the reason I wrote everything else is because everything else has one A and one B. So the count of the left parenthesis, for example, in this one is going to be the count of the left parenthesis of A plus the left parenthesis of B plus this one. That is all the way out here. So this is just going to be the left parenthesis of A plus the left parenthesis of B plus 1. And you should be able to see this argument applies for all of the other ones as well. And for a right parenthesis, a similar argument follows. We want to add all of the right parentheses of A and then B and then take this one. So it's going to be RA plus RB plus 1. And can we show easily that these two values are equal? This follows directly from our hypothesis. We assume that A and B are well formed, and so the number of left and right parentheses in them are already equal. So I can just make these substitutions. So if I replace LA with RA and LB with RB, it's just going to be the same value. So recalling on the process again, we prove it for the base step like so. And then we take an inductive step where we take any two arbitrary formulas and then we assume that they have the property that we are looking for. In this case, having an equal number of left and right parentheses. And we want to be able to show that applying one recursive step on that using any of these rules also provides a formula with an equal number of parentheses. So this question could ask anything. For example, prove that there is no well-formed formula with a conjunction at the end. And how are you going to prove this? Same argument. We're going to say no base case has an and in the end. So base case will be proved. We'll assume two variables p and q and then assume that they have no and at the end. And in the proof step, we'll argue that the only way to introduce an and between p and q is by using this rule. And applying this rule does not cause the and to go to the end. So by taking any two well-formed formulas p and q and applying one recursive step, there is no way to get a formula that has an and at the end. And mind you, this is just an example on the top of my head. We could use this technique to prove any kind of property about recursive structures in general. Alright, we'll do one more problem from language and alphabet. So we looked at the definition of length of a string yesterday, recursive definition of a length of the string. I'll just put it here for context. We said that the length of any word with its last character separated is equal to the length of the remainder plus 1. So this is our recursive definition for the length of a string. And then we had a base case that said that the length of the empty string lambda is just equal to 0. And to quickly recap how this worked, if we needed the length of a word like cat, we said that this will be the length of CA plus 1. Okay, so x is just this value and CA is the remainder. And this is again equal to the length of C plus 2. And this is equal to the length of lambda plus 3 because lambda represents just the empty string, everything is gone. And now I can apply the base case. I know that the length of lambda is 0. And see how we defined length in terms of length. But the problem size always reduces until we hit the base case. So this was the recursive way to handle length of a string. And today we want to prove a property about this length. So we want to prove that the length of two strings concatenated, length of xy, is equal to the sum of their individual lengths. And one very important hint, anytime that you're working with problems that involves alphabets and strings, you want your base case to relate to the empty string. We saw this in yesterday's lecture under recursive length and also recursive concatenation. Alright, so let's establish the base case for this one. So in the base case, I want to show that this is true if I substitute one of these variables with a lambda, with an empty string. Let me write that down and it will be clear why. I'll just write length of x lambda is equal to length of x plus length of lambda. I just need to prove this as my base case. And can I say that this is true? Let's try to simplify one more time. I know that x lambda is just x. And I know that from the recursive definition of length, the length of lambda is just 0. So Lx is equal to Lx. So the base case is true. Now I'll come back to why I started with x lambda for my base case. Remember, I need to reach this term xy. And length is recursively defined in a way that peels off the last character. So if you look into this example, in order to find the length of the cat, we peeled off the last character. And eventually we reached a state where we get a length of lambda. So I want the same thing to happen to y here. And I want to count for each character of y. That means I've started counting with all of x and nothing in y. And my idea is to introduce characters from y one at a time. So let us show the proof to make it absolutely clear. So like I just said, you should imagine one character from y coming into lambda one at a time. So when I apply this recursive definition, let's say k times, some characters in y would have been here. And then I would want to prove that upon bringing one more character, that is upon applying the recursive definition one more time, the length formula still holds. So in my proof, I'll just assume that for any arbitrary a that is replacing y, the length of x concatenated with a is equal to the length of x plus length of a. And using this assumption, I want to prove that if I introduce one more character, and that would be equivalent to saying the length of x a and some character c at the end is equal to the length of x plus length of a c. Now the proof from here is really simple, but it's really important to understand this concept. So we are saying if the length of x and something is Lx plus La, and I want you to assume that we are able to prove this. Let's say we are able to prove that the length of x and a with some extra character is also equal to the length of x plus length of that character. That would mean I can add one character at a time to build my length. Alright, so let's see how we can prove that this is true, provided that this is true. So we'll just start with the left hand side of this expression. We'll just write LHS is the length of XA and some character C. Now I know from the recursive definition of length that this is equal to the length of XA plus 1. And you can see this assumption here. I have assumed that length of XA is equal to length of X plus length of A. So I can just say this is equal to the length of X plus length of A plus 1. And the goal is to be able to get to this expression, which I can do in one more step. I'll just keep Lx the same. And from the recursive definition of length, I know that La plus 1 is the length of AC. So reviewing the process again, the question asked us that the length of any two words put together was equal to the sum of their individual lengths. We started by assuming a base case of y is equal to lambda, and that is the same as saying if I don't add this y to x, its length is not gonna change. So Lx is just gonna be Lx, and by using the property of the empty string lambda, I'm able to show that the base case holds. Now in the inductive hypothesis, I'm allowed to assume that the length formula works for any arbitrary choice. So if I just fix x and choose any arbitrary a instead of y, I can assume that the formula works. I have not proven it yet, I've just assumed that it works. But using this assumption, I need to prove that the length formula works even after I apply one more recursive step of the definition. We do that by considering one more character on the second word, and then this is the result that we want to prove. And we are able to prove exactly that by using the definition of the length as well as the inductive premise or the hypothesis from here. And I'll emphasize again, the core idea of understanding structural induction is far more important than grabbing one problem. Alright, we'll do one more problem in structural induction today and we'll be done for the day. Prove that for a full binary tree, the following inequality is true. And t is less than or equal to 2 raised to the power h of t plus 1 minus 1. So before we tackle this problem, let's understand a few details. N of t represents the number of vertices in a tree. So if I have a tree like this, you can see it has 5 vertices. And if I have another tree like this, so in this case it has 4 vertices as we can see here. And what will be the number of vertices of a new tree formed by merging these two? So that's the first question. See, when I merge, one new vertex is added because I need to add the vertex to connect it to the root of the previous vertices. So the number of vertices is whatever was first plus 1. So this is the first rule that I want you to remember. The number of vertices in trees t1 dot t2 by connecting two trees is just equal to the n of t1 plus n of t2 plus a new root element. And let's also quickly talk about the height of a tree. I want to draw 2 more children in here in order to demonstrate. So if I look into this tree up to here, I can see that this guy is kind of like at the ground floor at a height of 0. This is at a height of 1, height of 2, height of 3. So this tree has a height of 3. And if you look into this subtree, this only has a height of 2, 0, 1 and 2. And when I merge these trees, what's going to be the final height? We can see it's going to be 4, right? Because this level is 3 and one more will be 4. But how do we know 4? So we want to take the height of the maximum of the children. So this child had a height of 3. So 1 added to that is just 4. So if any root is connected to 5 previously existing trees, we want to check the height of each of them, find the maximum height and then add 1. And that will be the height of the new tree. So height of the combined tree t1 dot t2 is just going to be 1. And this is for the new age. And then we'll add whatever the maximum height was between t1 and t2. Alright, now we have some basic ideas about height of trees and number of vertices. We can tackle this problem. It is asking me to prove that the number of vertices is always less than or equal to this amount. So it says 2 raised to the power height plus 1 minus 1. And we are also given that the tree is full. So what does a full binary tree mean? Every node will have exactly 2 children or exactly 0 children. So there cannot be a node with only one child. Alright, so let's start with the base step. And in the base case, our goal is to prove that this inequality is true for the simplest tree. So if we consider a tree with just one vertex, R, we want this inequality to hold. So please mention this. For the base case, we are considering a vertex with only one node R. So let's now check this inequality. I know that the height of this tree is just equal to 0. And I can know from observation that the number of vertices is just 1. And then what is the inequality is saying? I can substitute. It is saying 1 is less than or equal to 2 raised to the power. What is the height? 0. 0 plus 1 minus 1. Now with some algebra, we'll be able to say 1 is less than or equal to 1. And since 1 is equal to 1, we say that the base case is true. Alright, now we'll aim for our recursive step. And again, coming back to the philosophy of structural induction, the goal here is to take any two binary trees, full binary trees that is, and then we need to show that if we apply one more recursion, that is if we take a new root and connect these two and form a new tree, this new tree will also hold the given inequality. So I'll just put the inequality here for better context. The number of vertices less than or equal to 2 raised to the power height plus 1 minus 1. Therefore, in the recursive step, I want to assume two trees that already have this property satisfied. So assume t1 and t2 such that the number of vertices in t1 is less than or equal to 2 raised to the power height of t1 minus 1, and the same thing for t2. So we are assuming that this is true. And what do we need to prove again? Now if we merge these trees t1 and t2, and that will be equivalent to applying one more recursive step, this new tree will still respect the inequality. So let me show my proof now. So I want to form a similar inequality for T1 dot T2. So let me get started with n of T1 dot T2. Alright, so what is the number of vertices of two trees merged together? We just looked at it. This is going to be n T1 plus n T2 plus one more root element. Now I want to do some substitutions. I know n T1 is related to this quantity and n T2 is related to this quantity. So let me just put the substitutions here. So for n1 and n2, I've just substituted these values here. And what do you think the sign should be here? Since the values that I've substituted are greater than the values that were already there, I can say this new quantity is greater. Alright, so continuing with the inequality, let us do a little bit of rearrangement for this step. So I want to write 2 raised to the power h t1 plus 1 plus 2 raised to the power h t2 plus 1, and then minus 1 and plus 1 is getting cancelled, but I still have 1 minus 1 remaining. And then I want to mention the height expression from earlier for easy reference. We knew that the height of two combined trees T1 and T2 would just be 1 plus maximum of their individual heights. Therefore, this value, the max height between h1 and h2, is something that I want. Now look at this carefully. These two things are not the same. Okay, this one has T1, this one has T2. But assume that they were the same, I could say this would be equal to 2 times the same quantity. If this and this is exactly the same, I can say this is 2 times the same quantity. And to be safe, I want to put whichever of these two is greater one here. So I want to say max of 2 raised to the power h of T1 plus 1 and 2 raised to the power h of T2 plus 1. And then I have a minus 1 here. And what will happen to this inequality? By the way, this is supposed to be a equals to, because this is just equal to the previous expression. Every time we write a sign, we want to relate to the just previous expression from it. So from here to here, I just rearranged. So this is just equal to. This is greater than the previous one. I hope you see. And in this particular step, I had this value and I had this value. I took a maximum of that and multiplied it by 2. So I can again put this sign for the inequality here. This is exactly the same as saying 4 plus 5. 4 plus 5, this is equal to 9. But if I choose the bigger of 4 and 5, so the bigger one is 5 and multiply this by 2, this will definitely be greater than 9. So in general, if I have a plus b and if I choose the greater of those and then multiply by 2, I'm going to get a value that is at least greater than or equal to the sum. And in case of inequalities, I agree that the substitutions always look arbitrary, but we always want to make those substitutions that take us towards our result. In this case, I need to somehow achieve height of T1 dot T2. And I see that the height requires maximum height of two trees. So the intuition will come with experience, but let us continue with the solution. Alright, so I'll just write 2 times. Now hear me out. I have 2 on the base, that is going to be the same. And the maximum of these two values will be obtained by simply taking the higher power of these two. So therefore I can take this as max of the height of T1 plus 1 and the height of T2 plus 1. And then I have a minus 1. And what is the sign in here? This time this is equal to, because it's just a rearrangement. Now continuing on, this is just 2 times, I'll leave it alone. And I have a 2. And on the power we'll do one more rearrangement, which it is the max of the heights of T1 and T2 plus 1. So I'm just taking whichever is maximum from T1 and T2 and just adding a 1. Because see, if I have a 7 plus 1 in one side and let's say a 9 plus 1 in another side, first I take the maximum of 7 and 9, that is just 9, and then add a 1. That will give me 10, and that is the same as choosing maximum between 8 and 10. So the max of something plus 1 and something else plus 1 is just the sum of whichever is greater plus 1. And then I have a minus 1. Don't want to forget that. And finally, if you look into this expression, this is the height of the tree combined with T1 and T2, right? Because I want added to the height for the extra root node, and rest of the height comes from whichever tree had a bigger height to start with. And finally, I'm able to say this is equal to 2 times 2 raised to the power the height of the combined tree T1 dot T2 minus 1. And if I apply the laws of indices one more time, I have 2 raised to the power 1 here and this whole thing here. So I can just add this is equal to 2 raised to the power height of T1 dot T2 plus 1 and then minus 1. So ultimately we started from here, which was the process of application of one recursive step to our two trees. And we had assumed that for our individual trees, the inequality would already hold. And then we combined our knowledge about height of a tree and the number of vertices to show that this merged tree T1 dot T2 also followed the inequality. And we are able to show that in this step here. So that concludes the discussion for today. So from the next video, we'll start having a look at recursive algorithms. So I'll see you guys in the next one. Have a good day and bye.